Hello friends, this is part 2 of question paper solution 2022 mathematical physics C8 paper. This is paper C8 of fourth semester under Dibrugarh University BSc paper, okay, physics honors. And this is my Insta ID. If you want to follow me, then you can follow me on Insta, okay. And before we start, please subscribe the channel, hit the thumbs up button, also share with your friends, okay. And in part 1 I have solved up to I have solved question number 1 and question number 2. Now we're going to start from question number 3, right? Question number 3. And link of the first part is given in the description box. If you haven't watched that, then go through that. And this is part 2, and hit the bell icon so that you get notified when next part will be uploaded, right? So now let's start. So here is the question number 3. What are the different types of singularities of a complex function, and name the singularities of this function, okay. So now you see, so what are the types of singularities? Generally, singularities are classified into two types. Those are isolated and non-isolated, right? So singularities, let me write singularities of a complex function, and this is the answer to question number 3a, okay. Question number 3a answer, let me write it properly, 3a, okay. So singularities of a complex function can be classified as number 1, isolated singularities, and number 2, non-isolated singularity. Non-isolated singularity. Then again, isolated singularities can be classified as number 1, removable singularity. Then number 2, pole, okay. Number 3, essential singularity. Essential isolated singularity. So these are the types of singularities, okay. So hope you have understood this. So singularities can be classified as isolated singularity and non-isolated singularity. Then isolated singularity, further it can be classified as removable singularity, poles, and essential singularity, okay. So now next part of the question, here you see this function. We need to find the singularities of this function, and locate and name the singularities of this function. Here you see, now you see this is the numerator and denominator, both of this function are polynomials, right? P of z, suppose this is h of z, let me represent that way. Both are polynomials. In that case, so we can obtain the singularities just by equating the denominator with 0 and those going to be poles of this function. Okay, so what is the kind of the singularity that going to be pole of this function? Okay, now let me clean this part. Just pause the video and note these things. This is the answer to question number 3, right? So this is the first part of the question number 3. So now let me cut it. So hope you have noted this, and let me write the next part of the question. The given function is here f of z to the power 8 plus z to the power 4 plus 2 divided by z minus 1 whole cube 3z plus 2 whole square, right? So just equate the denominator, that is z minus 1 whole to the power 3 and 3z plus 2 whole square with 0. In that case, then we can write z minus 1 whole to the power 3 is equal to 0, which implies z is equal to 1. As this is order of 3, we can say z equal to 1, 1 and 1, right, as there is whole cube. That means this is a pole of the given function of order 3. So this is a pole of order 3. You can write this is a pole of order 3. So similarly, we can obtain 3z plus 2 whole square is equal to 0, and that's going to be 3z plus 2 into 3z plus 2, that's going to be again equal to 0, which implies 3z is equal to minus 2 and z is equal to minus 2 by 3. And again here you see, as there is a power 2, so it is a pole of order 2. This is a pole of order 2, right? This is a pole of order 2, right? Suppose this function is analytic within this region, within this circle, closed curve C, suppose, then here you see these poles are such points that suppose z is equal to 1, this is suppose z is equal to 1, at which point this given function is not analytic, right? And this is suppose minus 2 by 3 is something somewhere we have here. Suppose this is 2. Okay, if this is 1, here you see, if this is z equal to minus 1, if this is minus 1, then if you divide it into 3 equal parts, then out of 2 parts, here this is going to be this point going to be minus 2 by 3, right? Z equal to minus 2 by 3. So hope you have understood this. This is real axis and this is the imaginary axis, right? So hope you have understood this. Now let's move on to the next question, that is 3b. So I have already solved this. Okay, I have already proved the Cauchy-Riemann equations in polar coordinates in the that is available in the playlist of complex variable. I'm going to provide the link of this answer. Okay, let me clean this, pause the video and note these things. Okay, so now you see, if you go to the description box, there must be written 3b answer. Okay, here links I have mentioned like this, links, and this is 3b answer. Here the link of that particular video will be given. Okay, so there you can find the proof of the Cauchy-Riemann equations in polar coordinates. Now let's move on to the next part. Here there are 2 questions. In question number 3, either you need to solve this one 3b, this one you have to prove this one, or you need to prove this one. Okay, as already it is done, that link of that lecture where I have proved this one, that is in the given description box, given in the description box. And now let's prove this one. Okay, so let me go to a new slide. So here is the question that we're going to prove now, right? So what we have. So let us consider this f of z. Let this f of z is equal to u plus iv. Let me consider that way. So mod of fz, that's gonna be root over u square plus v square, right? That's how we used to find the mod. Then if you square it, then it's gonna be equal to root over u plus u square plus v square whole square, and that's gonna give you u square plus v square, right? So first we have obtained this part, right? So now what we're gonna do, let us consider that this is equal to phi. Let us consider this is equal to phi. Say this is equal to phi. Then let's differentiate with respect to x. Let us differentiate this. Just do one thing. Let us differentiate this. This is suppose let me write equation number 1. Differentiating equation number 1 with respect to x. Then what we're gonna get? So we are to get here, you see, del phi by del x, that's gonna be equal to, if you differentiate it, then what you're gonna have, and that's gonna be 2u as again, then you're gonna have del u by del x, del u by del x. Then if you differentiate this v, then you're gonna get 2v, then del v by del x, because this u is not a function of x only, nor a function of neither a function of x nor a function of y. It may be function of both x and y. Okay, v is also function of both x and y. So now if you obtain the second order derivative, if you differentiate it again, then what you're gonna have? Again differentiating with respect to x again. So what we're gonna have? Second order partial derivative with respect to x. So again we're gonna get 2, and we're gonna apply here product rule. This is u and this is v. So u v, its derivative is given by u derivative of v plus v derivative of u. That's we're gonna apply, right? The first function derivative of the second function. If you differentiate it again, then what you're gonna have? You're gonna get second order derivative, right? Then the second function del u by del x, right? Then if you differentiate u, then again you're gonna get del u by del x, and that's gonna give you del u by del x whole square, right? So hope you have understood. So there must be a 2, so let's take the 2 common. Similarly, if you differentiate it again, then you're gonna get, and if you apply this rule, then you're gonna get 2, which is already taken common, then v, second order derivative of v with respect to x, then plus del v by del x whole square. That's what we're gonna have, right? So hope you have understood this, right? So now similarly we can find del phi by del y, right? If you differentiate this equation number 1 with respect to y, then again after obtaining this, again if you differentiate, then you're gonna get this, right? So I'm not gonna show that, just I'm gonna write similarly. Okay, so here you see, just pause the video and note it down. Okay, so now let me copy these things. Just wait. So let me manage here. So similarly what we're gonna have, if we obtain second order derivative of phi with respect to y, then here this simply just replace the x by y, then you're gonna get the desired result. Okay, so 2, everything's gonna be same, but instead of x we're gonna we're gonna replace the x by y. That's it. What we're gonna do. Then here we're gonna have v into this, then del v by del y whole square. That is what we're gonna have, right? So this is what we're gonna have. So this is suppose equation number 2, and this is suppose equation number 3. So let me write equation number 1, 2 and 3 in the next page. Okay, so these are the two equations, equation number 2 and 3. Now let me go back to the previous slide. Here you see on the left hand side we have this del x square del y square, right? And here we have plus, and phi is nothing but mod of f of z, square of mod of f of z, right? So this is nothing but phi. So that's why what we're going to do here, you see, let's add this equation number 1 and 2, 2 and 3, adding just simply, let me write simply like this way: equation number 2 plus equation number 3. If you add this 2, then what you're gonna have on the left hand side, you're gonna have this, right? And this part can be written this way. If you take phi common, you can use this as an operator, and which is operating on phi. You can take that way, and on the other side you can have 2 common again. Then write all these terms within this square bracket, or simply just do one thing. Let me copy this. Just wait, give me a second, just give me a second, let me copy this. Okay, so this is what you can have. Then let me rearrange it. Then plus, then right hand side of equation number 3. Okay, so we can add this way. Now let me copy this result, and let me go to next slide, as we have not enough space here. So this is the result we have got, adding 2 and 3, right? Let me write this way. Okay, so now you see here, according to Cauchy-Riemann equation, so what we're going to have, we're going to have this. This is Cauchy-Riemann equation, right? And what we can have, del u del y whole square is equal to minus del v del x whole square, right? So I hope you have already got the Cauchy-Riemann equations, and I have squared the Cauchy-Riemann equations here, right? So simply let me write here, squaring the Cauchy-Riemann equations. Sorry. Squaring the Cauchy-Riemann equations, we get these two equations, right? So and also we're going to use Laplace equation. Laplace equation, we can write let me use the black ink here, del second order derivative of u with respect to x plus second order derivative of v with respect to y, that's equal to 0. And similarly we can write second order derivative of u with respect to sorry, not u. So here you see that should be u. If this one is u, then the second one is also u. And then again second order derivative of v with respect to x plus second order derivative of v with respect to y, that should be also equal to y. Okay, so these two are Laplace equations. So now let me use these two results. This is suppose equation number 4 and this is 5. Let me take this pair of equations as equation number 5 and this pair of equations as equation number 6. Okay, so now let us use 5 and 6 in 4. Okay, now let me use 5 and 6 in 4. Then what we're gonna have? Okay, so what we can do here, you see here this equation number can be modified. Here you see this is u, this is also u. You can take u common, then what gonna be the result? So let me show you. Just wait. Let me just get some space here. Okay, so here you see this is the left hand side of the equation number 4, and this phi is nothing but mod of square of mod of fz, right? So we can replace the phi by this. Then if you take u common, then here you can have u within bracket second order derivative of u with respect to x, then plus second order derivative of u with respect to y, right? Then similarly plus if you take v common from these two, then what you're gonna have? V second order derivative of v with respect to x plus second order derivative of v with respect to y. Then you can write the remaining terms, right? Then you can write the remaining terms, and what are those? You can write del u by del x whole square plus, then you can write del v by del x, del v by del x whole square plus, you can write del u by del y whole square, del u by del y whole square, then plus del v by del y whole square. That's what you can write. So let me write this is equation number 4. So let me consider this is as equation number 4. Okay, so now what we can do now, let me scroll the slide to have enough space, right? So this is what we have got, right? So now you see from this equation number 6, if you use 6 in 4, then you can see clearly this term and this two must be 0, right? So this one is equal to 0, this one is also equal to 0 according to Laplace equation. So then what we can do here, using 5 and 6, 5 and equation number 5 and 6 in equation number 4, what we're gonna have? We're gonna have, let me write the left hand side. So here is the left hand side of equation number 4, right? Is equal to 2 within bracket. This first two terms are gonna be equal to 0. If you use equation number 6, then these two terms gonna be equal to 0. Then we have del u by del x whole square, then we have del v by del x whole square, right? If I am not wrong, right? Now here you see this del u by del y, del u by del y and del v by del y here. Those two can be replaced by del u by del x and del u by here minus del v by del x. Okay, just do one thing. On squaring this is going to be plus, right? So what we can do here, we have del u by del x whole square, then plus del v by del x whole square, then replace del u by del y. Del u by del y, this is replaced by minus del v by del x. On squaring it's gonna be del v by del x whole square, right? So del v by del x whole square, then plus again we can replace this del v by del y, del v by del y by del u by del x, right? So then what we're gonna have, del u by del x whole square, right? That's what we're gonna have. Now let's add these two, and let's add these two, and adding these two, what we're gonna have, let me copy this and let me go to a new slide. Okay, so then we're gonna get 2 del u by del x whole square plus 2 del v by del x whole square. Then we can take this common, take these two common, then these two gonna be 4, right? And this can be written as, this can be written as how? It can be written this way, root over just wait 4 card wicket under root, what we can write, del u by del x whole square plus del v by del x whole square, and this is square. On squaring this root gonna be removed, right? And here you see, we know that if f of z, since if f of z is u plus iv and mod of f of z is root over u square plus v square, then if you compare this one with this, this is u square plus v square, then you can write u plus iv as f of z, right? So you can consider this way, that you can consider this way, that mod of del u by del x plus I del v by del x, right, whole square, because mod of this, right, mod of this is equal to this one, right? So that's why mod of this, that's going to be equal to this one, right? And this is nothing but 4. So therefore what we can write, here you see, these things can be written this way, mod of del x of u plus iv, right? We can write that way, and u plus iv is nothing but, let me just cut it, this is nothing but f of z, and del x of f of z is nothing but f dash of x, right? So that is what we needed to prove. So we can write this way, just wait, there is a square, okay, this square is written here, okay, so we can write this way, just give me a second. So we can write del 2, so here, just wait, we can write the left hand side this way, which is already we have got as required for, then mod of first order derivative of f of z square. So this is what we needed to prove. So hope you have understood this. So now let's move on to the next question. So our next equation is this. Next question is this 3c. So state Cauchy's integral formula. Okay, that statement you're gonna get in the video that I'm gonna provide in the link. Okay, Cauchy's integral formula link. I have explained everything in a lecture that I'm gonna provide. A link of that lecture gonna be provided in the description box. I will write 3c answer, then there will be the link. Okay, I'm gonna provide the link of that video. So now let's come to this. Okay, how to solve this one. Now let us solve question number 3c. Here state the Cauchy integral formula. So as I have already said, that's gonna be the video where I have explained this formula, that is in the description box, link in the description box. So let's solve this part. So here we have integration sine pi z square plus cos pi z square divided by z1 minus z2 dz. Okay, and where c is the circle given by mod of z is equal to 1, right? So let me draw the circle here. This is the imaginary axis, this is the real axis, and here is the circle with the center at origin, because we have mod z only. So this point must be 1. This is the real axis, right? And this is the imaginary axis, right? So now, let's take the poles z minus 1 into z minus 2, equating these two with zeros. What are we going to have? We're going to have z is equal to 1 and z minus 2 equal to 0. That means z is equal to, which is outside the circle, because here the radius is 1, so it is 2, so 2 must be lying outside the circle, and 1 is on the circle. This is on C, right? So let me have some space here on C, right? So now, as you can see, z is equal to 2. Z is equal to 2 is outside the circle. So this expression can be written this way: integration on C sine n, sorry, not n, pi z square plus cos pi z square divided by, so as 2 is outside the circle, so that's why z minus 2 divided by z minus 2, and let me keep this one z minus 1 as numerator only, right? So dz. Okay, so now let me copy this. Okay, now let me go to a new slide. Here is the last step. Now you see, by Cauchy integral formula, if f of z is analytic, within or on the closed curve C, and if A is a point in or on C, then f of A is equal to 1 by 2 pi I integration along C f of z, z minus a dz, f of z by z minus a dz, and which can be further simplified this way, that integration f of z by z minus a dz is equal to 2 pi I into f of a. We can get this way. So by Cauchy integral formula, so what we're going to have, this is going to be equal to, this is going to be equal to, so we're going to consider this, we're going to consider this one as f of z, this one as f of z, okay, and compare this one with z minus a. Then what we're going to get, we're going to get just wait, so it will be better if we write this way, just wait, integration c here, let me write f of z and z minus 1 dz, that's going to be equal to 2 pi I f of, instead of a we have here 1, okay, so therefore here f of z is equal to sine pi z square plus cos pi z square divided by z minus 2, right? So therefore f of 1, that's going to be equal to sine pi 1 square, that means sine pi, then cos pi 1 square, that is cos pi, then 1 minus 2, right? So that's going to be equal to sine pi is 0, cos pi is minus 1, then again here 1 minus 2, that's going to be minus 1, right? So minus 1, that's plus 1. So let's put this value here, then we're going to get the result. So let me copy this and let me go to new slide. Here is the new slide. So what we have got, that is integration along c of f of z. F of z is nothing but this, right? So sine pi z square plus cos pi z square divided by z minus 2 divided by z minus 1 and dz by Cauchy integral formula, which is equal to 2 pi I f of 1, and value of f of 1 is 1, so we have got 2 pi I, that is the answer, okay. So that is what we needed to evaluate, right? So here you see this is nothing but this one, integration along c sine pi z square plus cos pi z square divided by z1 into z2, z minus 1 into z minus 2 dz, that is equal to what we have got, 2 pi I. So this is the answer. So hope you have understood. Question number 3D.